Hello everyone. So we have already discussed about the wave equation of a cylindrical bar while a projectile bar hits the cylindrical bar. So though that equation we derived and the analysis we did, it is not really very accurate. There are some additional considerations we need to take care of. So in today's lecture we will discuss about the additional considerations that we need to take care. So whatever we found in an earlier lecture, that elastic wave in a cylindrical bar, elastic wave in cylindrical bar is expressed as double second partial of u with respect to t e by rho second partial of u at respect to x, and where the velocity of the wave is v is e by rho. So now we will talk about the real situation, what happens when a striking bar or projectile hits the cylindrical bar. So this is our projectile, this is our projectile, and this is our cylindrical bar. So now this is moving at a velocity v, and it has a density rho naught and a naught. To remove any confusion, you can keep this wave velocity as c. So because here we are showing the projectile velocity is v, and rho naught and a naught are the cross section, mass density is the rho naught and a naught is the cross sectional area, and we assume that both the cylindrical bar and the projectile has are same material, the material are same, so that the density is same, and in this case we can take the cross section is also same. So what happens when a bar impact, suppose in this case in this figure we show the impact, this projectile hits the cylindrical bar. Now what will happen is, we will see in the third figure. So here there will be some stress pulses will be generated, the compressive stress. So compressive stress will go forward in this direction. Let us say this is the stress pulse, this stress pulse is going in this direction with a velocity c, and then similarly there will be compressive wave in the striking bar as well. The striking bar also, because the materials are also same, so with the same velocity there will be wave on the other side, in the other direction. So both compressive wave propagates in or we can write here c naught, c naught will be c naught is the wave velocity. So compressive wave with velocity c naught in both projectile and target, and target is this cylindrical bar is the target, cylindrical bar is the target. So now after some time what will happen is it will propagate more, and then this in the projectile bar, the wave will actually reflect in the free surface, this surface, and then it will return back. So, it will return back. So, this will reflect back with the same velocity, the reflection. So, at this end, reflection at this it will reflect, and at that time on the target also it will whatever it will travel in the projectile bar, and the same distance it will travel in the target bar as well, because the velocity are same. Now, in this case this is the total length of the pulse. We will see after some time this wave will go into the target bar, and there will be, let us say, no wave in the projectile bar. So, this wave, the length, that is the pulse, is now only in the target bar, and this length is the wavelength, which is can be represented with a capital lambda, and that is actually equal to twice L. So, L is the length of the projectile. L is the length of the projectile. Let us try to understand why it is twice L. When the wave reaches the projectile back end, so this end, so that is L. At the same time, the wave will travel L distance here, and when, because this is the velocity is same in the both the medium, because there is the same material, both the bars, the velocity is same. So, when it will reflect back from this end, and at that time it will also travel that much. Let us say this distance is x after it travels back, and similarly this distance will also be x. So, this till this point it is L, and the other point it is x. So, that means after the reflection, the stress wave, that the pulse has a actual total length of twice L, and that way it will go forward in this direction. So, now if we use the conservation of momentum, so for the prior to the impact and after the impact, so prior to impact and after the impact, so if you see prior to impact from the figure, so prior to impact it has a velocity v, and that can be written as prior to impact the momentum is equal to rho naught a naught L v. So this is the mass, and similarly after impact, so this rho naught a naught in the part of the bar which has the stress pulse is rho naught a naught into lambda, with we multiplied by the particle velocity. So, because that is the part of the bar only have the compression wave that is propagating towards the right direction, and that will give us, because lambda is equal to twice L. So, because the lambda is equal to twice L as we got in the previous figure, so this will be L UP. So, now if we use the conservation of momentum, so rho naught a naught L v is equal to twice rho naught a naught L UP. So, this will give us UP the particle velocity is half of the projectile velocity, and again from our earlier discussion, the stress generated in our earlier classes we have learned that this rho c up is equal to half of rho c v. Now this is that velocity of the wave, c is the velocity wave, and so up is v by 2 now. So we can express the stress generated by the impact. So stress generated by the impact with a projectile velocity v can be written like this. So we are discussing about additional considerations for elastic wave propagation in cylindrical bars. So this is important for split Hopkinson pressure bar experiments, which is the most widely used experiment for dynamic material testing. So it is important for split Hopkinson pressure bar experiment. Now the expected shape of the stress pulse is if it is in a simplified form. So the expected pulse shape is rectangular. It's rectangular. However, in real case, so we will get significant fluctuations. So in the real case it looks like something like this. So in real case it looks like this. So significant oscillation in real case. So these effects will influence the interpretation of the split Hopkinson pressure bar results. So these effects means this fluctuation effects, that is actually also called dispersion effect. So these fluctuations will influence how we interpret the split Hopkinson pressure bar results. And also so we will discuss how there are deviation from the simplified case. So initially what we got for uniaxial stress case, so we found that C naught, the wave velocity, can be expressed as square root of the ratio of elastic modulus by mass density E by rho. And however, in real case, in reality, so there are two effects. Number one is radial inertia and number two is wave interaction with external surface. Interaction with external surface. So let us first check what is radial inertia. So in the simplified case or simplified one or idealized one, so what we see that the stress wave, suppose in this longitudinal in this cylindrical bar there is a longitudinal stress wave. So we think that this compressive stress wave coming from left to right will compress the bar, suppose this small section, and that way the compressive wave travels from left to right. But in real case or in reality, so what happen is when the compressive wave travels from left to right, this section will be little expanded in the vertical direction. So that is, as you can understand, from Poisson's effect. So this is nothing but the Poisson's effect. So radial expansion with radial expansion or with axial compression. However, in the first case it is only assume that we have axial compression and no radial direction deformation. So basically, if you see the cross section, so let's the original cross section is the length is delta x and the diameter is d, and then the final shape will be like this, which is 1 plus epsilon, which is the strain, multiplied by delta x, and here our this will have the Poisson effect. So nu Poisson's ratio multiplied by strain, whole thing multiplied by d. So and in this case, because this is now elongated a little bit. So in this case we should understand that this is the strain is negative here actually, because this is a compressive strain. So epsilon is negative, which will have a axial compression and the radial expansion, and so we will have some inertial forces due to this radial expansion, that is material flowing outward due to the kinetic energy for this compression wave. So there will be some inertia forces. These are inertia forces along radial direction, delay the radial expansion. So that is what we meant with by this radial inertia. Okay, now we will talk about the wave interaction at the surface. So this so what initially we found is for a uniaxial stress case. So C naught is square root of the ratio of E by rho. For this is for one dimensional case, that is uniaxial stress. But if we assume 3 dimensional effects, 3 dimensional case, so there are different calculations. First one is we will talk about Rayleigh's calculation, and that gives us a Cp by C naught is 1 equal to 1 minus 3 Poisson's square pi square A by capital lambda whole square. So, Cp here is the phase velocity, here the phase velocity, which is nothing but the wave velocity in this 3-dimensional case. So, when we allow that multi-axial stress conditions. So, this phase velocity is normalized by C naught, which is for the uniaxial case, and nu is the Poisson's ratio, pi, and then A is the bar radius or cylinder radius, and then capital lambda is the wavelength. So, this is calculation proposed by Rayleigh, and the another one is proposed by Rayleigh, and then another one another calculation was proposed by Pochemer and Tree. So, this is another one. We are not will plot this, both of this. So, we do not include the equations for the second one. So, what we can see from here, so in three dimensional cases, so there are two, one is the Rayleigh and the another one is these two are commonly used calculations. So, in this case, so what we have is the phase velocity normalized by the uniaxial wave velocity. So, phase velocity is nothing but the wave velocity in the 3-dimensional case, and that can be also sometimes known as the group velocity, but the group velocity is can be different than phase velocity. So, we are not going into that details, but we want to know the simply the variation of the normalized the wave velocity for the 3D case with the ratio of bar diameter, so sorry, bar radius by the wavelength. So, the first one is the green that curve shows for Rayleigh prediction from this equation, whatever we found, we already mentioned this equation, and these dotted lines are for C1 by C naught, which is longitudinal wave velocity, and then C2 by C naught. We have already discussed about C1, C2 and the CS, which is the Rayleigh wave velocity. C1 is, we have found in the earlier lectures that lambda by twice nu by rho for longitudinal case, and C2 is square root of mu divided by rho, and CS will be little less than the shear velocity. So, the Rayleigh wave velocity is little less than shear wave velocity. So, now here we are showing that Rayleigh prediction for the 3-dimensional the case with the additional effects, and then we can see that if it is the A by lambda is very small, that means the bar radius is very small. So, this implies that Cp by C naught equal to 1, or they are almost the same. And then if for A by this A by lambda smaller than equal to 0.1, the Rayleigh corrections are accurate. Calculations are accurate. Now, we will see the second case, Pochemer and Tree calculations. We have not any included in equation, but we will plot it here. So, plot will look something like this will look something like this. So I am just smoothing this curve, the same curve. So it will look something like this, and this curve is Pochmer and 3 calculations. As I already mentioned that if a by lambda is less than 0.1, this Rayleigh predictions are also accurate, but otherwise if a by lambda is very high, the Rayleigh predictions are unrealistic for a by lambda high values, and in that case we can say that this Pochmer and 3 predictions are better. They are better than the Rayleigh the predictions. So you can see that at higher value of a by lambda, this PC which we call in short form Pochmer and 3 predictions or calculations actually approaches the Rayleigh wave velocity, which is like almost 0.58 times of C naught, which is almost 0.58 times of C naught. So whatever we told about C1, C2 and Cs, so as we discussed the dotted lines C1 for by C naught, that is normalized longitudinal wave velocity, and then C2 by C naught, and then again Cs by C naught, the dotted lines. Corresponding to C1, C2, Cs, which are I hope you understood from our earlier lectures, they are for unbounded media, and our C naught is for finite body. So C naught is for finite body with uniaxial stress. Then we will discuss about the wave interaction now. Wave interaction at free surface. So this is, let us say, the first case. So let us assume that we are hitting this cylindrical the rod with a projectile or striker bar, and then in the second case what we get to know that while this compression wave propagates, so there will be some waves that will the wave will interact with the free surface, and then there will be some waves will be reflected from the interface, and that is we call the release wave from the interface. So similarly, if we go for forward, so this wave will show like this, there will be release wave, and then similarly we have this, the wave will propagate more and more, and these release wave will interact among themselves. So these are the release waves. We have learned a little about the wave interaction earlier, reflection and refraction. So the release waves follow the main wave from the interface, will follow the main wave, main wave, which means, so this is the release wave and this one is the main wave, and they interact continuously and cause the fluctuation of particle velocity which we denoted as UP earlier. Fluctuation of particle velocity will lead to fluctuation of strain and stress as well. So that means in an earlier slide we have shown that this fluctuation, the stress fluctuation, so that is due to this release wave interaction, release wave from the free surface, okay, release wave from the actually I wrote here interface, but better we can write it as free surface, which is interface between the air and the cylindrical bar, but what we can write is a free surface. So these fluctuations can be predicted by computation. For example, R. Scalak has computed these stress wave predictions in 1957. He used a method of double integral transform using method of double integral transform to solve the problem of this impact of a cylindrical projectile on a cylindrical rod. Oh sorry, this particle velocity, I have made a mistake in the spelling. So particle velocity UP. So now we will discuss about another aspect of it. So what will happen when the cross section of the bar changes? Suppose we have a cross section of the bar, here is A1 and here the cross section is A2, and if we assume the materials are also different, then the mass density will be rho 1 here, the mass density will be rho 2, and similarly the wave velocity, if we say C1 here and C2 here, this is longitudinal wave velocity. So applying the force and particle balance, what we have used even earlier, force and particle velocity balance, so we can find the stress and particle velocity at the new cross section. So we will apply the force and particle velocity balance at the interface, and then we can find the stresses and particle velocity in the new cross section. So this analysis is important in split Hopkinson pressure bar, which we commonly abbreviated as SHPB. Generally we take the specimen as a smaller cross section or smaller diameter than the bar diameter, and also the material we test is let us say can be any ceramic or metal, and generally this is the SHPB specimen, and our bars are used in the SHPB are, let us say, very widely used bars are Merezing steel, high strength steel. So, then the properties will be different across the interface. So, as we can remember from our earlier lectures, so sigma transmitted by sigma incident is equal to twice rho b Cb divided by rho b Cb plus rho a Ca, where we know rho multiplied by C is the sonic impedance, we call it as a sonic impedance, and similarly sigma reflected divided by sigma I is equal to rho b Cb rho a Ca divided by rho b Cb rho a Ca. So, if we remember the earlier calculations we did in a previous lecture, that the equilibrium at the interface will require the inclusion of the area term. We did not do at that time, but now we can check that. So, what we had earlier, the equilibrium is equal to sigma I plus sigma r equal to sigma t, but now we have the different areas. So, sigma I A1 plus sigma r A1 equal to sigma t A2. So, if we use these equilibrium conditions, so we will end up with our expression sigma t is equal to twice of A1 rho 2 C2 sigma I is equal to A1 rho 1 C1 A2 rho 2 C2. Here it is important, this is A1 not A2 with rho 2 and C2 on the numerator, and similarly for sigma r, sigma subscript r, so this will be A2 rho 2 C2 A1 rho 1 C1 divided by A2, sorry, we can write first A1 rho 1 C1 plus A2 rho 2 C2 and multiplied by sigma I. So, which can be simplified as sigma transmitted is equal to twice A1 plus A2 sigma I, and sigma r equal to A2 minus A1 divided by A1 plus A2 sigma I. So, these are important for elastic wave propagation in cylindrical bars, which will be important for our split Hopkinson pressure bar calculations. Sorry, I made a mistake here, probably I forgot to mention this. So, this material 1 and we assumed in this case, these two cases, that material 1 and 2 are the same, material 1 and 2 are the same. So, that means rho 1 equal to rho 2 and C1 equal to C2. So, that will give these simplified expression for sigma t and sigma r. So, as we discussed that for split Hopkinson, the materials of the bar and the specimen will be different, and also can be the cross section can be different. So, With this, so we are closing this chapter of elastic wave propagation. So next we will discuss the plastic wave propagation.